Hello friends, in this class we will study maxima, minima or extreme points of a curve. So maxima and minima are functions of two variables. A function fxy is said to have a maximum value at x equal to a comma y equal to b if f of ab is greater than f of a plus h comma b plus k for small and independent values of h and k, positive or negative. A function fxy is said to have a minimum value at x equal to a and y equal to b if f of a b is less than f of a plus h comma b plus k for small and independent values of h and k, positive or negative. Thus fxy has a maximum or minimum value at point AB according as delta f, which is difference this f of a plus h comma b plus k minus f of AB less than 0 or greater than 0. Conditions for fxy to be maximum or minimum, or to have maximum or minimum value. So number one, if rt minus s square is greater than 0, then fxy has a maximum or minimum at point AB according as r is less than 0 or r is greater than 0. So function will have maximum when r is less than 0 and minimum when r is greater than 0, where r is equal to del square f upon del x square at AB, t is equal to del square f upon del y square at AB, and s is equal to del square f upon del x del y at AB. Okay, so if rt minus s square is less than 0, then delta f changes sign with h and k. Hence, there is neither a maximum nor minimum value at AB. The point AB is called a saddle point. Okay. If rt minus s square is equal to 0, no conclusion can be drawn about a maximum or minimum value at AB. Hence, further investigation is required. Now, procedure to find the extreme values of a function z is equal to fxy. So, first of all, find del x of z, okay, or f del y of z, or del y of f. Solve del x of z equal to 0, del y of z equal to 0 simultaneously. Okay, so this will give me points a comma b, c comma d be the solutions of these equations. Okay, so for each solution in step 2, find these values are, that is del square f upon del x square, s del square f upon del x del y, t is equal to del square f upon del y square. If rt minus s square greater than 0 and r less than 0 for a particular solution AB of step 2, then z has a maximum value at AB. If rt minus s square is greater than 0 and r greater than 0 for a particular solution AB of step 2, then z has a minimum value at AB. If rt minus s square is less than 0 for a particular solution AB of step 2, then z has no extreme value. It has a saddle point. It is a saddle point. Then AB is a saddle point, and if this is 0, then the case is doubtful and further investigation is required. Now coming to the examples, let us take a first example, this one. This is the given equation of the curve, and we have to examine the maxima or minima. So let fxy equal to this. So fx is this and fy is this. Simply partial derivative of this with respect to x and with respect to y. R is equal to fxx, that is 6x, t is 6y, s is minus 3a. So fx is equal to 0 and fy equal to 0, giving me this and this two equations. Now from the first equation I get y equal to x square upon a, and from y second equation y square minus ax equal to 0. So putting this value in equation number 2 here, I get this, for which either x equal to 0 or x cube equal to a cube, so which gives me x equal to a and x is equal to 0. Therefore when x equal to 0 and y equal to 0, and when x equal to a and y equal to a, we have 0 0 and a, two stationary points. So at 0 0, let us examine. So rt minus s square is giving me this minus 9a square, which is less than 0. Therefore this there is no extreme value at 0 0. Okay, the next point is a. So for this rt minus s square is 27a square, which is greater than 0, and therefore fx has extreme value at point a. Now let's check. R is equal to this 6a, okay, and replacing x by a, 6a, and r will be greater than 0 if a is greater than 0, and this r will be less than 0 if a is less than 0. So fxy has maximum for a less than 0 and has minimum for a greater than 0. Therefore fxy has maximum at a for a less than 0 and minimum at a for a greater than 0. Maximum value of function fxy, simply substitute these values like what are the values, a or minus a? These are a, okay, and substituting these values here, I get yes, when it is less than 0, then it is minus a, right? So therefore substituting this value, I get minus 5a cube. Okay, this is the maximum value. For minimum value, this a is positive and it is minus a cube. Question number 2, discuss the maxima and minima of this function. So this function is like this, and just expanding this, find fx, fy, partial derivative, first order partial derivative with respect to x and with respect to y. Then again finding r, that is fxx at av. It is not r, but it's the simple value of fxx. It will be r when we will substitute the value of x and y, which we obtain as stationary points, okay, by substituting fx equal to 0 and fy equal to 0. So these are simply fxx, fxy and fyy. And for stationary points, fx equal to 0, fy equal to 0. So I am getting two equations. Solving these equations, I get 0 0 and 1 by 2 1 by 3 as the stationary points. So at this point, okay, let us consider this point 1 to this 1 by 2 and 1 by 3. So at this point we get 1 upon 14, which is greater than 0, and r is minus 3 by 8. So it is simple indication that this point is the function has maximum at this point. Okay, so fxy has maximum at this, so hence maximum value is f1 by 2 1 by 3. Just substituting the value of x and y as 1 by 2 and 3 by 2 in the given equation of the curve, we get 1 upon 432. Similarly at point 0 0, rt minus s square is equal to 0. Therefore at 0 0, further investigation is needed. So consider delta f. Okay, delta f is nothing but f of a plus h comma b plus k minus f of a b. So this a is 0 and b is again 0. So we are left with f of hk minus f of 0 0, and if you try to find out this from the given equation of the curve, we get this. Okay, because f at 0 0 is 0, so just considering this term here and other terms like this, just multiplying. So these terms h raised to power 4 k square and h cube k cube, because h and k are already very very small, so these terms will be negligible, very small as compared to h cube k square. Okay, so we are left with delta f is this one. Okay, based on this we will try to determine the nature of delta f. So for any value of k, k square will be positive, only h will play a role because it is cube root. Okay, so for delta f is greater than 0 if h is greater than 0, and it is less than 0 if h is less than 0. So therefore delta f does not keep the same sign for small values of h and k, positive or negative. Therefore there is no extreme value at point 0 0. 0 0 is then the saddle point. Okay. Locate the question number 3. Locate the stationary points of x raised to power 4 plus y to power 4 minus 2x square plus 4xy minus 2y square and determine their nature. So similar way you will proceed, and these will be the stationary points and you can check the nature. Again, next question, question number 4. Examine for maxima, minima, maxima, minimum, maximum values of function f is xy equals sine x plus sine y plus sine of x plus y. So fx is this and fy is this. Simple derivatives. Similarly, you can find out r as t and then substitute fx equal to 0 and fy equal to 0. So just these are two equations from previous this fx and fy. Okay, just 2 minus 1 gives me this. So from here I get x equal to y. Just putting x equal to y in equation number 1, we get 2x equal to pi minus x, and this implies x equal to pi upon 3. So therefore x equal to y equal to pi by 3 is a stationary point. So that is pi by 3 and pi by 3. R is less than 0. If you put these values there in here, okay, you will get this less than 0 square root 3 minus square root 3, and s will be square root 3 upon 2. T is equal to minus square root 3. Therefore rt minus s square is 9 upon 4, which is greater than 0, and fx has maximum at this point. Therefore this has maximum at this point because r is less than 0. And maximum value of f is this, f of pi by 3, pi by 3. So simply substitute these values in the given equation. I get 3 root 3 upon 2. The next question, question number 5. Show that the rectangular solid of maximum volume that can be inscribed in a given sphere is a cube. Okay. What we do, let x, y, z be the length, breadth and height of a rectangular solid. If V is the volume of solid, then V is equal to x, y, z. X into y into z. Since each diagonal of the solid passes through the center of the sphere, therefore each diagonal is equal to the diameter. That is, let us take it is equal to d, and that is that becomes the yes, diameter, and therefore this d is nothing but this square root of x square plus y square plus z square, and just squaring this is equation of the sphere, and therefore from this equation I get z is equal to d square minus x square minus y square. Therefore we equal to this one, x, y into z. Z is this. Just expanding this, multiplying, we get v square like this, and Now we can find out, let us consider v square as f, and then we can find out the fx. So just differentiating this with respect to x, what we get? 2 times x d square y square minus 4 here and x cube y square plus 2 times x y raised to power 4. Similarly, we can find out fy, fxy, and we can find out the values of rs and t. So fx equal to 0 and fy equal to 0 gives me these two equations, this equation 1 and equation 2. So 1 minus 2 gives me this one, and y equal to x. So just substitute y equal to x in the equation 1, we get this, and from here we get x is equal to dy3, which is again equal to y. So therefore z becomes, just substitute these values in z, I get d upon root 3. So therefore this point A is dy3 and dy3. Rather, the values of x, y and z are equal, and those are d upon root 3. Again we can find out this r, okay, and which is less than 0. S is this and t is this, and rt minus s square is definitely greater than 0, d raised to power 8, and therefore v square, and hence v has maximum at this point x, y, z, okay, and when the solid is cube, that is when the solid is cube, because all these sides are same. Next question is, show that the function u equal to this has minimum value at a. Already given the stationary point, you simply have to check. So just find out fxx, or simple, that is uxx, uyy, uxy, find out rt minus s square, and then check whether this is, again, that is, it is greater than 0 and the value of r is positive, so it has minima at this. Question number 2, examine the following surface for high and low points, means simply for maximum and minima. So again doing the same thing, if you do it, it will be negative, so surface has no high or low points at this point. The next question is, find the minimum value of x square plus y square plus z square when ax plus by plus cz is equal to p. So for that, what we do, from this condition, we find out the value of z in terms of x and y, and put in the given equation. So I get this one, x square plus y square and z square is this one. So this is the value of fxy, the simple, not fxyz, but this is the value of fxy now, because we have substituted the value of z in terms of x, y. So the now f is a function of two variables only. So find out first order partial derivative with respect to x and y. These are the partial derivatives. For extreme points, this equating these to 0, we get those two equations. So solving these two, I get x equal to this and y get this. Now again you can find out fxx like this and fyy this, and fxy will come out to be this. Then when you find rt minus s square, it will be this one, which is greater than 0. So therefore, and r is fxx at this point, and again that is already, if you see previously, this r will be this, and it is again positive, and therefore this has minimum value at these points, these critical points, okay. Therefore minimum value of f is this one. If you substitute these points there in the given equation of the curve, you will get this, okay. And the next question, find the dimensions of rectangular box open at the top of maximum capacity. Capacity means volume, whose surface is 432 square centimeter. It's given. So let xyz be the dimensions of the box and s be the surface. Then the surface area is given by this equation, okay, because it is open at the top, so that will not be considered. So otherwise, in other areas of other surfaces will be multiplied by 2. and we get this, and v is x, y, z, and we have to maximize this v. What we will do, we will find out the value of z in terms of x and y, and then we will substitute in the given equation. We get this, so v is this. So find out this, the derivative, partial derivative of v with respect to x as well as y, and just equating that to 0. So I get this equation as well as this equation. Okay, 4 and 5. So equation this if I subtract 5 equation from 4, I get this one, y equal to plus minus x. So just neglecting the negative value because we are talking about the positive quantities, distances. Okay, so substituting y equal to x in 5, I get y equal to 12. So therefore x equal to 12 and y equal to 12, and from this equation of z, if we put these values of x, y here, I get z equal to 6. So yes, now I have the stationary point now, and we can find out vxx, vyy, vxy, and we can compute rt minus s square. It will be greater than 0 and r will be less than 0 at this point. So hence the dimensions of the box are 12, 12 and 6, and at which the volume of, or the capacity of, that rectangular box will be maximum. Okay, so yes, yes, I think there is one more question like this one. A rectangular box open at the top is to have maximum volume of 32 cubic feet. To determine the dimensions of the box requiring least material for its constructions, mean least or minimum surface area. So here this S is this, and we know this surface area is this, and the volume is given vxyz equal to 32. From here z is equal to 31 xy, and s is equal to this. So therefore s is equal to this one. Now we have to find out del del x of s and del del y of s. So if we solve this, we find x equal to y equal to 4. Putting x, y equal to 4 in equation 2, we get z equal to 2. So this point 4, 4 rt minus s square is greater than 0, r is also greater than 0. Therefore s is minimum or having minimum at 0.44. Therefore the dimensions are 4, 4 and 2. So thank you very much. This completes the whole topic of maxima and minima.